All right, hey, Cedarville University. This is Mr. Wagner's lecture on the periodic chart. This should be the last one before your final exam. Let's go through this stuff together, and we'll learn some things. Here's some pictures of Shiloh, and here's Shiloh and Elsie. Okay, moving on. If you want to access the periodic chart, all you got to do is Google it. You can find all sorts of different places to find all sorts of information. You can use pt1.com, places like that, to find the periodic chart. The first person that we need to talk about is this handsome gentleman up here, Dmitri Mendeleev. Here's a little history lesson on the periodic chart. He published the first version of the periodic chart in the Journal of the Russian Chemical Society in 1869. Of course, you don't need to remember the journal and you don't need to remember the date. The person, however, yes, this is important. He arranged the periodic chart according to atomic mass. Why didn't he use atomic number? Because they hadn't been discovered yet. The neutrons, the protons, no one knew about those yet. All they had was atomic mass. So he arranged things according to atomic mass. At that time, there were only 63 elements that we knew about. And when he arranged all the elements, they kind of fell into some groups based on their properties. Now, that in and of itself is not particularly genius. And here's kind of like a version of the periodic chart that he first created. No big deal. Almost anyone could have done that. They arranged all 63 elements in a particular way. But the very interesting thing is, if you follow my pointer right here and right here, he actually left spaces in the periodic chart for elements that had not yet been discovered. Because he arranged them in a way that was predictable based on their properties, we can actually find out all sorts of information about these elements with not even having them discovered yet. And that is the genius of Dmitri Mendeleev. So due to Mendeleev's arrangement of the elements and the properties of the elements, they were predictable. Mendeleev left gaps in the periodic chart. That was the genius. No one had done that before. No one had left gaps in the periodic chart before. He was able to predict the properties of elements that had not yet been discovered. So imagine this. He's saying there's some elements out there. No one's found them yet, but I'll tell you all about the elements. That was the genius. And he said the elements, if arranged according to their atomic weights, which is the only information he had at the time, exhibit an apparent periodicity of properties. There's a video that I'm going to link. It's a TED-Ed video about Dmitri Mendeleev. I highly suggest watching it. It's going to put all this in a lot of context. Yes, it's about 4 or 5 minutes. Please, please, please watch this video. It'll put Dmitri Mendeleev and his discoveries in context. So after Dmitri Mendeleev comes along this handsome fellow right here. His name is Henry Moseley. Henry Moseley, he used X-ray spectra to determine the number of protons in an element. Why is this a big deal? If we know the number of protons in an element, now we can arrange the periodic chart like this. 1, which is hydrogen. 2, which is helium. 3, which is lithium. 4, beryllium. 5, 6, 7, 8, 9, 10. So imagine you arrange the periodic chart. It goes 10, 11, 13. Wait, 10, 11, 13, we must have missed one. So now, without a doubt, by arranging everything according to atomic number, we can find out which elements we may have missed and which ones we didn't miss. So by the age of 26, Henry Moseley, he rearranged the periodic chart according to atomic number, which is a big deal because he kind of helped discover some of the proton stuff. He wasn't the only one, and we remember that from previous lectures. And he arranged the periodic chart according to atomic number. That made it easy to predict which elements had not yet been discovered, but there's some sad news because Henry Moseley was supposed to be the next Einstein. This guy was genius. I mean, what was I doing by the age of 26? Certainly not discovering how to arrange the periodic chart. So after doing all this, by age 26, at a very young age, he went to war in World War I, and he was shot and he was killed in the Battle of Gallipoli. Again, that's not going to be on your test. His age is not going to be on your test. Potentially the name Henry Moseley and his contribution to science might be on your test. That he rearranged the periodic chart according to atomic number. So let's talk about the arrangement of the periodic chart. You see the columns that go up and down. These columns that go up and down, we can call them groups or families. I prefer to call them families, but they can go by either. You can call them groups or families, and they go up and down on the periodic chart. Elements in a family, they share certain physical and chemical properties. This is kind of silly, but it makes good sense. Is there anything that this family has in common? I see something. It's the same thing when it comes to the periodic chart. The families of the periodic chart have things in common. That's why I like to call them families, because they have things in common. And you're probably asking about this big yellow section. We'll get to that later. But yeah, these families, they have things in common. That's why they're called families. On the other hand, the horizontal rows that go side to side, those are called periods. And the properties of elements, they gradually change as you go across a period. So we've got this red one right here is period 1. The orange is period 2. The yellow is period 3. The green is period 4. And we just give them numbers. So there are 7 periods on the periodic chart. 1, 2, 3, 4, 5, 6, which includes these, and 7, which includes these. So that makes them 7 periods on the periodic chart. Pretty sure there's some questions about periods and families on your test. So periods indicate the number of electron shells. If you remember talking about atoms, we said that atoms, they have layers of electrons. I'm going to call those electron shells, those layers of electrons. Well, guess what? Family number 1, it has 1 electron shell. That's both helium and hydrogen. Family number 2, there are 2 electron shells. Family number 3, 3 electron shells. Family number 4, 4 electron shells, and so on. So you get it. So let's practice here just to see, make sure we're on the right track. So which family contains boron? You might want to use your periodic chart for this. Take a look at your periodic chart. Which family is it? Keep in mind, family goes up and down, and there should be a number at the top of your periodic chart. It's family 13 that contains boron. So it goes family 1, 2, and then the smaller families are 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. And then, so family 13 contains boron. Which one contains sodium? Which family contains sodium? Its symbol is Na. It's on the far left side of the periodic chart. It's, I already told you the symbol is Na. It's in family number 1. Which family contains iodine? It's a little bit further towards the right of the periodic chart. Iodine's in family number 17. Now, instead of talking about the families, let's talk about the periods. Which family contains, or I'm sorry, not which family, which period contains scandium? Yeah, period 4 contains scandium. Which period contains fluorine? Period 2 contains fluorine. Take a look at your periodic chart, find arsenic. It's a little bit further down, it's towards the right. Which period contains arsenic? Period 4. So did you get them all correct? Did you? Don't lie. Did you get them all correct? You're a nerd. Just kidding. So let's talk about the representative elements here. The representative elements are families 1, 2, 13 through 18. So take a look at all this stuff in purple here. This bright purple. Those are the representative elements. We treat those ones separately than the yellow ones and then the green ones. They're kind of in their own category. So we've got the representative elements here. These are the tall families. And then the transition metals are in the middle. They're the smaller families. And then intertransition metals, those are the green ones down at the bottom. Anyway, let's keep going. Let's talk about the transition elements. The transition elements are the ones in the middle. Oh, look, it says representative elements. Sorry, we need to switch that. The transition elements are families 3 through 12. It's the transition ones, the ones in the middle. It's not that they're less important. It's that when they behave, they don't necessarily have the same trends as the families and the representative elements. So we kind of treat them as their own separate group. But they fall in the middle of the periodic chart, and we'll see why in just a little bit. So when it comes to the arrangement of the periodic chart, the periods indicate the number of electron shells. I think we already mentioned this. So period number 1, it's got 1 electron shell. You see the circle in the center? That indicates the nucleus. So family number 2, we've got 2 electron shells. We've got 2 rings of electrons. Family number 3, we've got 3 rings of electrons. So notice, when you look at this periodic chart, the transition elements have been removed. So like I said, we treat the representative elements separately. So they remove the transition elements in this particular case. All right, let's keep going. Let's do a stop and check. You're going to want to use your own periodic chart. I highly suggest you do this and follow along, because it's going to help reinforce some things. So how many energy levels does cobalt have? Find cobalt on the periodic chart. It's a transition element, so it's in the middle part. But how many rings of electrons does it have? 4. It should have 4 rings of electrons. How many energy levels, or how many rings of electrons, does boron have? Notice it's in period 2. So period 1 is helium and hydrogen. Period 2 contains boron, so that means it's going to have 2 rings of electrons. How about iridium? You got to look a little bit further down. Symbol is IR. For iridium, how many energy levels does it have? Well, it's not in period 1, not in period 2, 3, 4, or 5. It's in period 6, so that means it has 6 energy levels. I misspelled helium here. Apparently I put a 1. Kind of gave the answer away. How many energy levels does silver have? Silver, remember, it's a transition element. It's in the middle. Its symbol is Ag. So how many periods down is it? Is it period 1, period 2, period 3? It should be in period 5. And since it's down in period 5, that means it's got 5 rings of electrons. So here's the electron cloud structure. And the thing is, do you need to memorize all these numbers? You do not. You simply need to know that whatever period it's in on the periodic chart will determine how many rings of electrons there are. So scientists have discovered that electrons within the electron cloud have different amounts of energy. In other words, electrons in this inner ring right here, they have the least amount of energy. Electrons way out here, they have the most amount of energy. So the further they are from the nucleus, the more energy that those electrons have. Let's keep going. The electrons closer to the nucleus have lower amounts. We're just kind of restating what I told you. Closer to the nucleus, low energy. Far from the nucleus, lots of energy. Let's keep going. Oh, less energy. I just learned how to do some of those. It's fine. Well, okay. Let's talk about the role of electrons, because electrons are pretty important things. The periodic trends in the table are the result of electron arrangement. So that's one of the reasons why the periodic chart looks the way that it does, is because of the way that the electrons are arranged. The outermost electrons in the outer ring, we give those a special name. These are valence electrons. So you see, here's the nucleus. Here's the first ring. We know this element has to be in period 3 because it's got 3 rings of electrons. And the outermost ring are called valence electrons. So those are valence electrons in the outermost ring. Anyway, let's keep going. So electrons occupy energy levels in specific patterns. We kind of already said this. The group or the family of the element determines how many valence electrons there are. Not how many rings, but how many valence electrons there are. Let's take a look at a pattern here. And by the way, it says the period or the row of the element determines how many electron levels, but the family determines the number of valence electrons. Take a look at family number 1. 1 valence electron, 1 outer electron. What about lithium? 1 outer electron. What about sodium? 1 outer electron. What about potassium? 1 outer electron. Let's go all the way over here. This is technically group 18, but since we removed the transition elements, we can call it group 8. But this is 2, that's the exception. But neon, 8 outer electrons. Argon, 8 outer electrons. Krypton, 8 outer electrons. What about oxygen? It's in family 16. Here we call it group 6 because we removed the transition elements. But oxygen, yeah, so I made a mistake. I had to edit it. Group 6, which is actually 16 on the periodic chart. Notice oxygen has got 6 valence electrons, sulfur 6 valence electrons, selenium 6 valence electrons. So the family determines the valence electrons. The period determines the number of electron shells. Okay, so that is something that is important. And here's a video on electron configuration. Let's keep going. When it comes to valence electrons, this is just a visual to help us out. Everything in family number 1, 1 valence electron. Not 1 electron total, 1 valence electron. I'm talking about the outermost electron. Family number 2, 2 valence electrons. Family 13, because we're skipping all these ones. Family 13, 3 valence electrons. Family 14, 4 valence electrons. Isn't this happy? It just makes sense. So we can determine how many valence electrons there are by looking at the family. And the valence electrons determines how it reacts with things. That's kind of a whole nother wormhole that we're not going to go down. But let's take a look, and I highly suggest that you do this. Follow along with your own periodic chart. It says how many energy levels does beryllium have? Notice you're looking at the period, and when you look at the period, it'll tell you. So the answer to this one is 2 because it's in period 2. So beryllium, it's in period 2. That means it's got 2 electron shells. How many energy levels does rubidium have? You got to look a little bit further down. Rubidium has 5 electron shells because it's in period 5, not family 5. It's in period 5. What about lead? Lead is in period 6. So it's got 6 valence electrons. And lastly, silicon, it's a little bit further to your right. Silicon, it's got 3 electron shells because it's in period 3. So remember, the period determines the number of electron shells. But now let's talk about valence electrons. So those are the outside electrons. How many electrons are in beryllium? You have to see what family it's in. So take a look at your periodic chart, see which family it's in. It's in family 2. And since it's in family 2, it's got 2 valence electrons. What about sulfur? A little bit further to the right on your periodic chart. Sulfur has 6 valence electrons because it's in family 16. How many electrons are in the outermost layer of neon? Hint, it's all the way to the right on your periodic chart. It's in family 18. So how many valence electrons does it have? It has 8. And how many electrons are in the outermost layer of boron? Boron's in period 2, but what family is it in? It should be in family 13, so therefore it has 3 valence electrons. It's got 3 valence electrons. All right, let's keep going.